A Harvard astrophysicist believes there's a strong likelihood this is a craft of alien origin, and the implications obviously for humanity.
Imagine a comet, not like any we've ever seen, soaring through space from a distant star system. A giant with a tail defying the very laws of physics. A comet that shouldn't exist, yet here it is, breaking every rule we thought we knew about the universe. 3I Atlas isn't just a discovery, it's a cosmic anomaly, one that's left the world's brightest minds in shock and uncertainty. What's really happening out there, and why is this strange visitor making its way toward us?
A third interstellar object just entered our solar system. It's called 3I Atlas, discovered by NASA's Atlas telescope in Chile. Its velocity and hyperbolic path shows that it is not from our solar system.
NASA's recent discovery of the interstellar object 3I Atlas was not meant to rewrite the rulebook. In fact, it was initially thought to be another routine observation of a passing cosmic visitor. However, as the data began to be analyzed, some of the findings were anything but ordinary. A quantum AI, designed to process vast amounts of astronomical data, flagged several anomalies in the object's behavior that had even veteran astronomers scratching their heads. The most striking of these oddities was the object's sun-facing tail, which broke the established rules of physics that govern comet behavior. Such a feature is not supposed to happen according to current scientific understanding. Interstellar objects are rare, with only 2 others ever having been confirmed before 3I Atlas, Oumuamua in 2017 and Borisov in 2019. These objects are fascinating because they are visitors from beyond our solar system, coming from other star systems. However, the behavior of 3I Atlas has raised questions that go far beyond the usual mysteries of a comet. Its motion, composition, and physical properties seem to defy everything we thought we knew about these objects. The initial observations of 3I Atlas, taken through NASA's Atlas survey, revealed some striking anomalies. For example, the comet was found to have a tail that faced the sun, which goes against the conventional understanding of how comet tails form. Typically, a comet's tail points directly away from the sun, driven by radiation pressure, the force exerted on particles by the sunlight. This force pushes dust and gas outward, away from the sun, forming a trail that's easily detectable, but in the case of 3I Atlas, the tail was facing directly toward the sun. Such an observation suggested that something was happening to this object that didn't align with what astronomers have observed in the past. NASA's imaging teams worked to calibrate the stacked exposures from their survey to pinpoint the exact location and movement of 3I Atlas. Each pixel of data contained vital information about the object's trajectory and size. What they found was even more surprising. The object's nucleus was far larger than expected for an interstellar visitor. It appeared to be at least 0.3 K in size, and could even be as large as 5.6 K, a massive body when compared to other interstellar objects. Oumuamua, the first such object discovered, was likely only about 200 meters in length, while Borisov was around 1 kilometer long. 3I Atlas could be 5 times larger than that, or more. The fact that 3I Atlas was so big, so active, and so close to Earth raised a number of questions. The probability of detecting an object of this size and activity traveling through interstellar space was statistically incredibly small. Most interstellar objects remain hidden, either too faint to detect or lost in the glare of distant stars. Yet this one was picked up on a routine survey. The data chain is clear. And from the initial discovery by Atlas to follow-up observations using NASA's Hubble and the James Webb Space Telescope, JWST, every image confirmed that this was indeed a single, solid body with an unusually large core. The object's brightness ruled out the possibility of small debris or fragments that could have been mistaken for an object. This was a monolithic body, not a collection of smaller parts. The discovery was puzzling not only because of the object's size, but also because of its location. 3I Atlas was traveling through the solar system in a way that defied expectations. For an interstellar object to end up so close to the sun's orbit with its large size and distinctive features was statistically improbable. The chances of an object from another star system randomly being ejected and passing so close to Earth's orbit are extremely low. Yet there it was. It seemed to be following a specific path, one that was anything but ordinary. As scientists began to map out its trajectory, they realized that the object was moving in a direction that brought it dangerously close to several of the major planets in the solar system. The calculations showed that on October 3rd, 2025, 3I Atlas would pass within just 28 million kilometers of Mars, about 0.19 astronomical units. This distance, although it may seem vast in everyday terms, is actually very close in astronomical terms. For a comet to pass this close to a planet, especially one coming in from interstellar space at 58K/s, was highly unusual. Only 4 weeks later, 3I Atlas would swing past the Sun at its perihelion, its closest point to the Sun, reaching its maximum speed of 68 km per second. On November 3rd, it would come within 0.65 astronomical units of Venus, a distance inside Earth's orbit. Such close passes are exceedingly rare for any comet, let alone one originating from outside the solar system. What made these close passes so noteworthy was not just the distance at which they occurred, but the gravitational effects they could have. As 3I Atlas passed by Mars and Venus, the gravity of each planet would subtly tug on its path, slightly altering its trajectory. This is a known phenomenon in space science, where planets exert gravitational assists on passing objects. Spacecraft engineers use this effect to increase a spacecraft's speed or alter its direction. However, the odds of such a sequence happening randomly, without any planning, are infinitesimally small. It seemed as though 3I Atlas was following a path that was too precise, almost as if it were being guided or influenced in some way. Despite the unlikely odds of this particular path, the data from NASA's calculations confirmed that this is exactly what was happening. Each close pass by a planet was accurately mapped with the distance, velocity, and angles carefully calculated. The object's path seemed almost too perfect to be purely accidental. Some astronomers began to wonder whether there was a deeper unknown force at work, influencing the object's movements in a way that conventional physics couldn't easily explain. The object's movement and trajectory were one thing, but there was also something deeply unsettling about its composition and behavior. Spectroscopic analysis, which scientists use to study the light emitted by an object, revealed even more inconsistencies. Normally, when a comet is discovered, astronomers look for specific chemical markers in the spectrum of light. These markers, such as cyanogen and diatomic carbon, are the typical chemical signatures of a comet's icy core. They glow brightly when the sun's heat causes the comet to wake up and release gases. However, in the first weeks after 3I Atlas was discovered, none of these typical signatures appeared. The spectrum was almost completely blank, where the usual signs should have been visible. This absence of typical comet markers was baffling. The dust was present, visible in images, but there were no clear signs of the usual comet gases. It was as if the object was behaving in a completely unexpected way. As the comet approached the sun, faint traces of cyanogen appeared, but they were delayed and still did not fit the normal patterns. This delay, combined with the sunward dust tail and lack of chemical signatures, deepened the mystery of 3I Atlas. As scientists continued to observe 3I Atlas, it became increasingly apparent that the object was behaving in ways that defied typical comet physics. The first major anomaly was the comet's tail, which was facing directly toward the sun. Normally, when a comet gets close to the sun, the heat causes the icy nucleus to release dust and gas, forming a tail that points away from the sun. This phenomenon is a result of radiation pressure, the force exerted by sunlight on the dust and gas particles. As the sun heats up the comet, the radiation pressure pushes these materials away, creating a tail that extends in the opposite direction. However, with 3I Atlas, something strange was happening. Instead of the tail being pushed away from the sun, the dust seemed to be clinging to the sunward side of the comet. This was a major deviation from the expected behavior of a comet. The fact that the dust was facing toward the sun rather than being pushed away from it posed a challenge to the understanding of how cometary tails are formed and how they behave. Standard models of comet physics simply could not explain this anomaly. The tail should have been pointing away from the sun, and yet it wasn't. This wasn't just a minor deviation, it was a fundamental contradiction to the laws of physics as they were understood at the time. At first, researchers wondered if the tail might be a result of the comet's unusual shape or its rotation. Comets are known to be irregularly shaped, and it's possible that the way 3I Atlas was spinning or tumbling could have caused the dust to be distributed in an unexpected manner. However, this explanation didn't hold up either. When scientists looked at the data more closely, they found that the object's behavior couldn't be explained simply by its physical shape or its spin. It seemed that something else was at play, something that was not accounted for by the conventional understanding of cometary behavior. To make matters even more puzzling, spectroscopic scans of 3I Atlas revealed further inconsistencies. Spectroscopy is a powerful tool used by astronomers to study the chemical composition of celestial objects. By analyzing the light emitted or reflected by an object, scientists can identify specific chemical elements or compounds that are present in the object's composition. When a comet is active, astronomers expect to see certain chemical signatures in the light spectrum, namely the presence of gases such as cyanogen, diatomic carbon, and other volatile compounds. These gases are released when the sun's heat warms the comet's icy core, causing the ices to sublimate and escape into space. In almost every active comet observed, these chemical markers are readily detected. The presence of cyanogen and diatomic carbon is considered a signature of the comet's activity, as these compounds are produced when the comet's ice begins to vaporize. However, when astronomers first observed 3I Atlas, they found that there were no clear signs of these typical comet gases. The spectrum of light emitted by the comet was almost completely blank, with no traces of cyanogen or diatomic carbon to be found. It was as if the comet was not behaving like a typical comet at all. This was highly unusual, as the absence of these gases is rarely seen in comets, especially in the early stages of their approach to the sun. The fact that 3I Atlas showed no signs of the usual chemical signatures was baffling. It wasn't just that the gases weren't detected, it was the complete lack of them. It was as if the comet was not releasing any material at all in the way that a typical comet would. In the early weeks after the discovery, there was no evidence of the characteristic gas emissions that astronomers typically associate with comets. The dust was visible, and it appeared to be behaving in a way that was consistent with a comet, but the usual chemical markers were missing. This created an even bigger mystery for scientists, as it suggested that 3I Atlas might not be composed of the same materials as typical comets. As the object continued its journey toward the sun, faint traces of cyanogen began to appear. But they were delayed, and still, the chemical response didn't align with the dust activity. The appearance of cyanogen came much later than expected, and it was weak, failing to match the usual patterns seen in other comets. This delay in the appearance of the gas was another red flag. In most comets, the release of gases occurs almost immediately as the comet gets closer to the sun, but 3I Atlas didn't follow this typical pattern. The late arrival of cyanogen and the absence of other chemicals made the behavior of the comet even more perplexing. There were several possible explanations for these anomalies, but none of them fully accounted for all the data. Some researchers suggested that the comet's surface might have been covered by a thick layer of crust that had formed over billions of years in interstellar space. This hardened surface could have shielded the comet's inner ices from the sun's heat, preventing them from vaporizing until much later than usual. This idea seemed plausible, but it didn't explain everything. For one thing, if the comet's surface was covered by such a thick crust, it would still need to release material in some way, and yet no obvious outgassing or jets of vaporized ice were observed. Other scientists speculated that the comet's spin axis might be locked in such a way that only certain regions of the nucleus were exposed to the sun at any given time. This could explain the delayed release of gases, as different parts of the comet would become active at different times. While this idea could account for some of the anomalies, it still didn't explain the sunward-facing tail and the complete absence of certain expected chemical markers. As the comet continued its journey, the contradictions only became more apparent. The object seemed to be defying all the conventional laws of comet behavior. The dust that streamed sunward, the absence of volatiles, and the delayed chemical response all pointed to something that didn't fit the usual models. And yet, despite these puzzling signs, 3I Atlas was clearly a comet. Its dust trail, although strange, was unmistakable, and its movement through the solar system suggested that it was on a typical cometary trajectory. The anomalies in the data prompted astronomers to search for new explanations. Some researchers proposed that the unusual behavior of 3I Atlas could be due to its unique composition. Perhaps the comet was made of materials that were unlike anything seen in the solar system, substances that behaved in ways that defied conventional understanding. Others suggested that the object's size and mass might be contributing to its odd behavior. With the nucleus much larger than other known interstellar objects, 3I Atlas could be experiencing forces that other, smaller comets did not. Despite all the theories, the fact remained that the object was behaving in ways that simply couldn't be explained by current models of comet physics. As the mystery deepened, scientists began to question whether the usual explanations for cometary behavior were adequate to explain the peculiarities of 3I Atlas. It was clear that something more was at play, something that researchers had yet to fully comprehend. For now, the enigma of 3I Atlas continued to challenge everything astronomers thought they knew about comets, interstellar objects, and the fundamental laws of physics. With each new observation, the puzzle grew more complex, and the search for an explanation pushed further into uncharted territory. As scientists continued to gather data on 3I Atlas, one of the most intriguing aspects of the object was its sheer size. Early observations from NASA's Atlas survey revealed that 3I Atlas was far larger than any previous interstellar object, possibly as large as 5.6 kilometers in diameter. This was a significant finding, as it made 3I Atlas an exceptional object in the context of known interstellar visitors. For comparison, Oumuamua, the first interstellar object ever detected, was estimated to be no more than 200 meters long, while Borisov, the second such object, was around a kilometer in size. The size of 3I Atlas made it not just large for an interstellar object, but also one of the largest comets ever discovered. The discovery of 3I Atlas was already remarkable due to its origins, as it came from outside the solar system. However, its size and the data that followed further added to the anomaly. The vast majority of interstellar objects that pass through our solar system are far smaller and less active than 3I Atlas, which made it all the more unusual. It wasn't just that the object was large, it was that it was also incredibly active. This led to questions about the object's origins and how it had managed to travel so far across the galaxy without being detected. Until now. In addition to its size, the trajectory of 3I Atlas raised eyebrows in the scientific community. When astronomers first calculated its path, they realized that the object was heading for a close encounter with several planets in the inner solar system, including Mars, Venus, and even the Sun. This was highly unusual for an interstellar object. Most interstellar objects, when they pass through the solar system, remain far from the Sun and the planets, barely interacting with the solar system at all. However, 3I Atlas was on a trajectory that would bring it remarkably close to Mars and Venus, which meant that its path through the solar system was anything but ordinary. On October 3, 2025, 3I Atlas was expected to pass within just 28 million kilometers of Mars, a distance that, while significant, is considered close in astronomical terms. For a comet coming in from interstellar space, this was an unusual event. As most comets typically pass by planets much farther away, 4 weeks later, 3I Atlas was set to pass the Sun at its perihelion, the closest point to the Sun in its orbit, reaching speeds of up to 68 km per second. These close passes by both Mars and the Sun were already raising concerns among astronomers. But the trajectory of the comet did not stop there. On November 3, 2025, just a few weeks after its perihelion, 3I Atlas would come within 0.65 astronomical units of Venus, which is inside the orbit of Earth. This close approach to Venus was even more unusual, as it was rare for a comet to pass close to a planet in the inner solar system, let alone one from outside the solar system. These close encounters were not just statistical anomalies. They were highly significant events that required careful analysis. The trajectory of 3I Atlas seemed almost calculated, as if it had been directed by some force to thread a narrow path between the inner planets. As scientists examined the object's trajectory more closely, they realized that the gravitational effects of the planets were subtly influencing the comet's path. This is a well-known phenomenon in planetary science called gravitational assist, where the gravity of a planet can change the trajectory of a passing object. For spacecraft, this effect is often used to speed up or alter their course, as spacecraft engineers can plan for it years in advance. However, for a natural object like 3I Atlas, the odds of such a precise gravitational assist occurring by chance seemed extraordinarily low. The fact that 3I Atlas was passing so close to Mars, then to the Sun, and then to Venus, within a matter of weeks, suggested that there was more at play than just chance. Scientists quickly realized that the close encounters between 3I Atlas and the planets were not just random events, but part of a series of gravitational interactions that seemed almost too perfectly timed to be coincidental. The comet's trajectory was being subtly altered by the gravitational forces of Mars and Venus, causing its path to bend in ways that would have been impossible if the object were simply passing through the solar system without interacting with the planets. The precision of these close encounters, coupled with the timing of the events, led some astronomers to consider the possibility that 3I Atlas trajectory was not purely random, but rather the result of some unknown factor. At this point, the odds of 3I Atlas's precise trajectory were being calculated using simulations and probability models. The results were staggering. Out of hundreds of thousands of random simulations, fewer than 0.005% of trajectories could match the specific sequence of events that 3I Atlas was following. This suggested that the chances of such a sequence of events occurring by chance were vanishingly small. The idea that a comet from outside the solar system would pass so close to Mars, then Venus, and then continue its journey toward Jupiter, all within a few months, seemed more improbable with each new calculation. The precise alignment of these encounters led to even more questions. For instance, the gravitational assist effect was acting on 3I Atlas in a way that seemed almost too calculated. The object's trajectory was bending in response to the gravitational forces of the planets, but the path it was following appeared to be carefully choreographed, as if the comet were threading its way through the inner solar system with pinpoint accuracy. The chances of this happening by accident seemed extremely remote, and astronomers were left wondering if there was more to the story than they had initially thought. As the mystery of 3I Atlas deepened, some researchers began to question whether the object was actually following a path that was determined by natural forces, or whether there was some unknown influence at work. Could it be that the object's trajectory was being guided by something more than just gravity? The possibility that 3I Atlas was following a purposeful route through the solar system raised the stakes of the investigation, and the search for answers became even more urgent. In addition to its unusual trajectory, the object's size, activity, and precise path all pointed to the idea that 3I Atlas was not just another random interstellar object. It was something much more significant, and its behavior raised questions about the nature of interstellar objects in general. Could there be other objects out there following similarly improbable paths, just waiting to be discovered? Or was 3I Atlas a unique object? One that had managed to slip through the cracks of our detection systems until now. Where now the mystery of 3I Atlas remained unsolved. But the object's journey through the solar system had already raised important questions about the nature of interstellar objects, their trajectories, and the forces that govern their movement. The closer 3I Atlas came to the inner solar system, the more scientists realized that this object was unlike anything they had ever encountered before. Its large size, unexpected activity, and improbable path through the solar system had already made it one of the most intriguing objects in recent astronomical history. The next few months would be critical in solving the mystery of 3I Atlas, and astronomers were determined to get to the bottom of what made this interstellar visitor so exceptional. As the data on 3I Atlas continued to come in, researchers began to analyze it more deeply using advanced computational tools. The object's unusual behavior, combined with its odd chemical signatures and trajectory, prompted a closer inspection of its properties. At the heart of the analysis was the work of artificial intelligence, particularly a form of quantum AI that had been deployed to sift through the vast amounts of data collected from multiple sources. This AI was tasked with identifying patterns and anomalies that might have been overlooked by human researchers, and it quickly flagged several unusual features of 3I Atlas that warranted further investigation. One of the most striking findings from the AI's analysis was the detection of periodic signals in the light curve of the comet. A light curve is a graph of the intensity of an astronomical object's light over time. Typically, a comet's light curve will show a gradual change in brightness as it moves through the solar system, with occasional peaks and dips due to factors like changes in the amount of sunlight the comet is receiving, or variations in its activity levels. However, in the case of 3I Atlas, the AI detected a repeating cycle in the comet's brightness, a tight, consistent periodicity that was unlike anything seen before in a comet. This periodicity was not the random flickering of light that might occur as the comet passed through turbulent areas of space. It was not the slow fading light of a comet drifting away from the sun. Instead, it was a precise and regular cycle, almost like a heartbeat buried in the noise. The AI's algorithms detected this pattern with a level of precision that would have been difficult for human astronomers to spot. Periodic signal persisted night after night, even as the overall brightness of the comet changed with its distance from the sun. The implications of this discovery were profound. The regularity of the periodicity suggested that there was some underlying physical process driving the changes in brightness. This was not simply an artifact of the instruments or an irregular fluctuation in the comet's light. It was a real signal, one that pointed to something more fundamental happening within the comet. The fact that the AI was able to isolate this signal from the background noise and identify it as a genuine anomaly was a major breakthrough in the study of 3I Atlas. At first, scientists were unsure what to make of this discovery. The periodicity did not match the expected spin rate for a nucleus of the size and composition of 3I Atlas. It also didn't align with any known orbital resonance or periodicity associated with comets. This left researchers with a growing sense of unease. Could the signal be a sign of something new? Something entirely unknown? Was there a deeper explanation for the comet's behavior that had never been considered before? As the AI continued to analyze the data, it flagged another anomaly that added to the mystery of 3I Atlas. Researchers had been monitoring the object's trajectory, measuring its position over weeks, and trying to map its movement through the solar system. They quickly realized that the comet was not following a path that could be explained by gravity alone. The acceleration data showed a small but measurable deviation from what was expected. The comet's movement was not behaving in the way that conventional models of comet physics predicted. This deviation, although tiny, was statistically significant and suggested that some other force was acting on the comet, nudging it off its expected path. At first, the most obvious explanation for this unexpected acceleration was outgassing. When a comet approaches the sun, its icy nucleus begins to heat up, causing the ices inside to sublimate and turn into gas. This gas can then escape from the comet in the form of jets, which can push the comet in the opposite direction, causing it to accelerate. This phenomenon, known as the rocket effect, is well documented in many comets and has been observed numerous times. However, in the case of 3I Atlas, there was a problem with this explanation. The usual signs of outgassing, such as spikes in the levels of cyanogen or diatomic carbon, were not present in the early data. In fact, the expected outgassing signatures appeared much later than they should have, and when they did appear, they were weak and didn't seem to match the expected pattern of acceleration. This presented a problem. If outgassing wasn't responsible for the acceleration, then what was? The unexpected deviation in the comet's trajectory suggested that there was something more complex at play. Some researchers began to propose more exotic theories. One possibility was that the comet's surface was covered in a thick, hardened crust, possibly formed over billions of years of exposure to cosmic radiation in interstellar space. This crust could be masking the usual outgassing process, delaying the release of gases until much later than expected. This would explain why the comet's acceleration occurred before any clear signs of outgassing were observed. Another possibility, though more speculative, was that 3I Atlas's nucleus might be unusually thin or reflective. Some researchers suggested that the object could be behaving like a natural light sail. In this scenario, radiation pressure from the sun would act more efficiently on the object, causing it to accelerate in a way that was similar to how a spacecraft with solar sails is propelled by the pressure of sunlight. This theory was still in the realm of speculation, but it was an intriguing possibility, as it suggested that the comet's behavior might be fundamentally different from anything seen before in a comet. Despite these theories, none of them fully accounted for all the data. The mystery of 3I Atlas was growing deeper, and researchers began to realize that they were facing an object that was unlike any comet they had ever studied. The AI's analysis, the periodic signals, the unexplained acceleration, all of these factors pointed to something extraordinary. But what was it? Some researchers began to entertain even more radical ideas. What if 3I Atlas wasn't just a cosmic fluke, but a sign of something more unusual, something that we didn't yet understand about interstellar objects? Could the object be the remnant of a much larger body, shattered long ago? and now drifting as part of a much larger interstellar flotilla. This theory, though still speculative, suggested that 3I Atlas might not be a single object at all, but rather the tip of an iceberg, a fragment of a much larger cosmic structure. Theories continued to emerge, each one attempting to explain the strange behavior of 3I Atlas, but none of them could fully account for all the data. The AI's detection of periodicity, the unexpected acceleration, and the absence of the usual cometary markers all pointed to a mystery that was far from solved. For now, the object remained an enigma, and scientists were left to ponder what 3I Atlas really was, where it came from, and what it might be telling us about the nature of interstellar objects. Despite the lack of definitive answers, one thing was clear: 3I Atlas was challenging our understanding of comets, interstellar objects, and the forces that govern their behavior. As new data continued to pour in, astronomers were forced to consider new possibilities and question long-held assumptions. With each new discovery, the mystery of 3I Atlas grew more profound, and the search for answers took scientists deeper into uncharted territory. For now, the object remains a cosmic puzzle, one that may take years or even decades to fully solve. But the journey to uncover the truth about 3I Atlas is just beginning, and with it, the potential for new insights into the universe's most mysterious and unexplored corners.